Today's focus is on physical versus chemical changes and chemical reactions. So, in order to understand physical and chemical changes, you really need to understand various properties of matter. And properties of matter are characteristics that enable us to distinguish one kind of matter from another. So, what is different about hydrochloric acid from water? Both are liquids, both are clear, but hydrochloric acid does not react in the same way that water does. So that would be a difference in property of its matter. So there are basically two types of properties. There's physical properties and chemical properties. A physical property can be observed or measured without changing a substance's composition. So basically, composition means what it's made out of. Okay, so I can observe it without changing what it's actually made out of. So if I talked about somebody's hair color, it's brown. That would be a physical property. Chemical properties can only be observed by changing the composition of the material. You actually will change its identity or what it is made out of at the atomic level. So a chemical property is something that you are literally changing its composition in order to see. So here are some examples of physical properties. Melting and boiling point. A lot of people don't understand that that's a physical property, but in order to melt something, I'm not literally changing what it is. I may change what it looks like, but in essence, I'm not changing what it is. So melting point, I am going from a solid to a liquid. For example, if it was water, I would go from ice to liquid water. It is still made out of H2O in order to melt, so therefore it is only a physical property. Color, as long as it's not changing color. Density, malleability. Malleability is being beaten into thin sheets. So can it be malleable? Can it be beaten into thin sheets? So a classic example would be aluminum foil. Conductivity, does it conduct electricity? Is it magnetic? And how hard is it? Some chemical properties are, can it rust? Does it decay? Can it burn? Can it ferment? Or can it react with such and such? So let's go through some properties of water. So water expands as it freezes. So what is changing? It's expanding, but it is freezing. So this would just be a physical change or physical property because it is not changing what it is made out of. Hydrogen peroxide, which they give you the formula of H2O2, can decompose, ooh, that word decompose, to produce water, which everybody should know is H2O. So is H2O2 the exact same thing as H2O? No, so therefore it changed, so that would be a chemical property. Water boils quicker in Denver, Colorado than at the beach. Boiling is just a phase change, meaning it's going from a liquid to a gas, but it is still water in both states, so therefore it would be a physical property. When an electrical current is passed through water, so once again, you have to know that water is H2O, elemental hydrogen and oxygen are produced. So I'm going to be making some hydrogen and oxygen. Is H2O the exact same thing as H2 and O2? No, it's not. It does change what it's made out of. These are no longer bonded. Hydrogen is no longer bonded to that oxygen like it is in water. So therefore, this would be a chemical change. Salt can dissolve in water. Dissolving is a very classic one that students definitely get confused on. And the reason why they get confused on is because they think it totally disappears. But it is completely reversible, and all we have to do is evaporate off the water. So it hasn't actually changed what it's made out of, and we get the salt back. So this would just be a physical property. Now, those are properties, these are changes. I sometimes use these interchangeably. They're very few different. They are different, but in the whole scheme of things, I really want you to understand physical versus chemical compared to change versus property. So a physical change will change what it looks like, so it's physical or its visible appearance, but you're not changing the composition of the material. So changes the affect the physical properties only, you do not change the composition. That is the key for a physical change. A chemical change, on the other hand, changes the composition of the substance, meaning you are creating something entirely new. So some examples of physical changes are boiling, melting, freezing. Notice that they're very similar to the properties that we were talking about. Crack, dissolve, crush, diffuse, condense, cut, split. Okay, so all of these change what they look like. They're either smaller pieces or they're not in the same state of matter, such as solid or liquid. But if we broke down to and went down to the chemical composition of that substance, it would still be the same. Chemical changes are usually not reversible, so that's kind of a key to look for. But what you're really doing is you're literally changing what it is made out of. So anything rust, tarnish, digest, explode, ignite, cook, burn, any of these super reactive things, those would be examples of chemical changes. I do like to understand one key when you're dealing with physical changes is any state of matter change, such as boiling, freezing, condensing. Triangle means change, by the way. Any state of matter change would be a good example of physical change. Another one that students get is dissolving. That's another one that they get confused at. And with chemical changes, really understand that anything particularly where you're cooking, baking, burning, anything with that, those are really going to be chemical changes. All right, so there are 6 signs of chemical changes that you guys want to understand. And my rule of thumb is that generally speaking, if you see 2 of these, then it's going to be a chemical change. So if you see both a color change and gas being produced, it probably is going to be a chemical change versus a physical change. So what are those signs? You have color change, you have gas production, so you see bubbles, you see a temperature change, and that can be both going up in temperature or going down in temperature, light being produced. Okay, so you literally see light, a precipitate being formed, which we'll talk about, and irreversibility, which means you cannot easily be reversed. Now, one thing that a lot of people think of irreversibility is like ripping of paper. Is ripping of paper a physical or a chemical change? Well, it's not easily reversed, and taping it isn't really doing it. But did I actually change what it was made out of? No, I did not. So that would not be a chemical change. We're going to go over a precipitate, but if you ever see a precipitate formed, that is a guaranteed sign that a chemical change occurred. You don't even have to worry about anything else. As long as you see a precipitate being made, you are good to go. All right, let's talk about that color change. So as soon as you see a color change, such as cooking an egg, where you go from clear to white, that would be an example of a chemical change. Sometimes you'll go from yellow to clear, or you'll go from a yellow to a white substance. That is a sign of a chemical change. Gas production. So what I want you to understand is that bubbles are being produced, and that's the gas being produced, or you'll notice a new odor. Okay, an odor is gas being released also. But make sure that it's not due to you adding heat to it and you're going through a phase change, such as boiling. Okay, so boiling is not an example of a chemical change because you are actually adding the heat, and that is what is causing the bubble production, not bubbles doing it on its own. Temperature change, heat is given off or absorbed. A classic example would be a fire. Ice melting, this is not a really good example. What I would always think of is an ice pack. So if you, like those disposable ice packs, so if you break open that seal and it starts becoming cold without you actually adding or taking away heat on your own, that would be a sign of a chemical change. Hot packs are also the same thing as long as they're those disposable ones that you have to like kind of crack open. Light being produced. So fireworks or a match, those are all great examples of how you would see light. Things that are glowing, that is also typically going to be a chemical change, such as a glow stick. Precipitate. So this is what's crazy. A precipitate is known as a solid. Okay, a precipitate is a solid. It's not like water, it's not precipitation. But what is happening with a precipitate is you actually have 2 liquids that are clear. Now, they could be colored, but they are totally see-through. And what happens is when you combine those 2 liquids, what you'll get is a liquid, but you'll also get something that is cloudy. When it is cloudy, that is a solid. So right here on this thing, in this beaker, you have 2 clear liquids. That's a clear liquid and that's a clear liquid. And where they meet, you actually get a solid. A solid is anything that's cloudy. So if I ever have, like let's say milk, okay, any liquid where you can't perfectly see through it, there is something solid floating in it. So milk has solids floating in it. When you look at pond water, that has solids floating in it. Why? Because it's cloudy, and that cloudiness is actually caused by a solid. So anytime you have a precipitate form, automatic going to be a chemical change. So those are the 6 signs of chemical changes, and what they lead to is causing a chemical reaction. Now, in order for you to understand a chemical reaction, you need to understand chemical energy. Remember, chemical energy is the energy that's stored in bonds of atoms or molecules. And if I break or make these new particles and I change their chemical energy, I am going to be doing a chemical reaction. You do need to know a few terms. So first off, that you have reactants. We always read a chemical reaction equation, which is this guy. Okay, here's your chemical reaction equation. We always read it from left to right, just like we do in English. Okay, so we always read left to right. Anything to the left of the arrow is going to be deemed as a reactant. A reactant is the stuff that you are starting with and you are utilizing. It is your initial stuff. You are reacting these reactants. Then you have an arrow and that separates your reactants from your products. And then you have your products. Your products are always, always, always written to the right of the arrow. And these are what you produce. So products are what you make or what you produce. Now, if you have two reactants or two products, how you separate them is by a plus sign. So this plus sign represents that it is separating the two guys on the right-hand side, which are your two products. So I only have really one reactant, which is water, on the left-hand side, but I, in essence, make two different products of hydrogen and oxygen on the right-hand side, and I do need to separate them by a plus sign. Now, it is key for any chemical reaction that you understand that the products created will be entirely different from the reactants that you started with. Why? How do you know this? Well, looking at this guy, water, a liquid, stuff we drink, okay, can produce hydrogen and oxygen. Water is not flammable. Both hydrogen and oxygen are extremely flammable. They are also gases, so they no longer have the same properties that they started with. Okay, as water. So they completely change when you have a chemical change going on. So in this one, what I want to go over is identify the reactants and products of each equation. So once again, how you do it is you just look at what is the reactant. Those are the guys to the left of the arrow. So I look at my arrow right here, and these guys would then be my reactants. This is a visual. The next one is just a visual of your reactants, your products. And so anything to the left of the arrow, once again, would be deemed as your reactant. These guys would be two reactants of two different compounds. And here would be my reactants on the left side. Once again, all you have to do is look to the left of the arrow, and that's how you get your reactants. Now, once again, to re-emphasize, I have a plus sign. It separates my two reactants from each other, my two reactants from each other, my two reactants from each other. And because I only have one reactant in this guy, I don't have to worry about having a plus sign. Now your products, on the other hand, are going to be to the right of the arrow. So to the right of the arrow, I've got two waters, I've got this guy, I've got these two compounds, and then I produce two with those guys. So once again, reactants, products, super easy. Reactants are always to the left of the arrow. Arrows always go from left to right pointing, and then everything to the right of the arrow are your products. As a rule of thumb, you also have to obey, for written chemical equations, the law of conservation of mass. And the law of conservation of mass states that during any chemical reaction, matter is neither created nor destroyed. What that basically translates to is that the mass of your reactants has to equal the mass of your products added up. All right, so what does this law mean? So we're just going to do a few example problems. First off, looking at these reactants to these products. Okay, how do I know? Because it's to the left of the arrow and the right of the arrow. I need to be able to understand what these little guys mean. First off, to understand this guy right here tells me what state of matter it is in. So the G stands for gas, L would stand for a liquid, S stands for a solid, and AQ stands for aqueous, which we really won't get into in this class. These little guys are subscripts. What that does is tell you how many of that particular type of atom are inside that molecule. If I do not see a subscript, like for this carbon right here, where I have CH4 and I don't see a subscript after that C, it is an understood 1. Just like I typically won't write in algebra 1x, I just write x, it's an understood being there. So in CH4, I have 1 carbon and I have 4 hydrogens. If I look at CO2 on this side, I have 1 carbon and 2 oxygens. The big numbers are known as coefficients, and coefficients are what you do in order to balance a reaction. How do you know you're balanced? You're going to literally have the exact same amount of carbons on the left as you do on the right side of the arrow. Same amount of hydrogens on the left as you do on the right-hand side of the arrow. Same amount of oxygens on the left as you do on the right-hand side of the arrow. So these coefficients tell me how many particles of each one I have in a reaction. So that if I don't see, just like the previous one where if I don't see a number, it is an understood one. So because I do not see a coefficient, it is an understood one. Whereas in this CO2, it would also be an understood one. If I asked you about, let's say, O2, okay, and this guy right up here, it would have a 2, which means I would have 2 of these oxygen molecules floating around for every one of these CH4 ones going around. So here's a translation of what it's all saying the exact same things, 1, 2, and 3, just in different forms. So this is my chemical equation of CH4 going with O2, going to CO2 to H2O. I then translate it into words to saying what it is. So methane gas reacts with oxygen to form carbon dioxide gas and water. And then we do a visual representation of these chemicals. So if I were to visualize, this is my carbon. These are each of my 4 hydrogens. Okay, these are each oxygen. Each oxygen, notice I need 2 oxygens, so that's why I have 2 of these guys. But I overall need 2 also, so that 2 represents that oxygen and that oxygen. So once again, this 2 subscript refers to how many within each compound I have or molecule, and this 2 refers to how many total of them I need. CO2, here's my 1C, here's my 1, 2 oxygens. And then for H2O, here's my 2 H's and my 1 O for each H2O. But then this 2 represents how many of those guys I need. Okay, this is what we would call as a balanced reaction, and that takes into account the law of conservation of mass. So how does this picture show that particles and therefore mass is conserved from reactant sides to product side? Is that we have an equal number of each atom on either side of the reaction. So what I'm talking about is that if I look at this guy, okay, oxygen, I have 1, 2, 3, 4 with circles with X's on the left-hand side, and I have 1, 2, 3, 4 on the right-hand side. As far as the clear circles, I have 1 and 1 on each side. And then as far as the dark black circles, I have 1, 2, 3, 4 on the left-hand side or the reactant side, and I have 1, 2, 3, 4 on the right-hand side. So that's what it's saying is that I have an equal amount on both sides. What is all that really happens to the particles in the chemical equation? What is happening is that they are just being rearranged and bonded to new things. And then number 3, can atoms of one type be changed or transformed into atoms of another type during a chemical reaction? And the answer is no, it cannot. Okay, so if I start with 4 hydrogens, I have to end with 4 hydrogens. These hydrogens can't turn into, let's say, heliums. Okay, during chemical reactions, they cannot change into a new element. So let's put this into actually mathematical terms. So remember, the law of conservation of mass states that the mass of the reactants is equal to the mass of the products. So if I get one of these problems, what I'm going to want to do is put underneath them what it's actually talking about as far as masses go. So if 16 grams of CH4, so I know I'm starting with 16 grams of that, completely reacts with 64 grams of oxygen, what is the mass of the products that I should be forming? So according to this, my mass of the reactants equals my mass of the products. So all I have to do is add up my mass of the reactants, and they are going to equal the total mass of both of these products. So what is 16 plus 64? You get 80. So I know that my products should also equal total 80 grams. Now we are not expecting you to understand and figure out how many grams of CO2 you'd make versus how many grams of H2O. Just total, it would form 80 grams. And our final example is if 8 grams of CH4, so I'm going to write down 8 grams right below that, react completely with oxygen, and 22 grams of CO2 and 9 grams of water form, how much oxygen is consumed? So according to my formula of mass of reactants is equal to my mass of my products Okay, I'm going to say my mass of my reactants is equal to my mass of my products. So if I solve it, 8 plus x is equal to 22 plus 9, which is 31. Solve for x, which means I'm going to subtract 8 from both sides. So x equals 23 grams. So I know that oxygen would be contributing 23 grams to make this balanced out. Hopefully you have a complete understanding after tonight about physical versus chemical changes and properties, how to identify a chemical change with their 6 signs, and the law of conservation of mass, where mass is neither created nor destroyed, which translates to my mass of my products have to equal the mass of my reactants.